So we look up at night, right? And you see all those stars, these little points of light. They feel so permanent, like they've been frozen there forever.
Yeah, the very comforting thought, that constancy.
But, well, what if I told you that even those seemingly fixed lights are actually moving in really subtle ways? And modern astronomy, the really cutting edge stuff, is letting us see these tiny, tiny shifts.
That's exactly it. Today, we're doing a deep dive into something called perspective acceleration in astrometry.
Okay.
It sounds a bit technical, but basically it's all about how a star's actual journey through space creates an apparent change in how we see its position in motion from, our viewpoint here on Earth.
Huh. Like watching a plane fly overhead. Even if it's going straight, it looks like it speeds up and slows down as it passes.
Exactly like that. A perfect analogy. Its actual flight path is steady, but its apparent motion changes from our perspective.
Cool. And for this journey, we're using an excerpt from some material focused on the Gaia mission, right? The space telescope.
Right. That's right. Specifically, a part that really unpacks this perspective acceleration idea, especially now that we can measure star positions with such insane accuracy.
So what's the mission for you, the listener, today?
Well, our goal is to figure out why radial velocity, that's the star's speed, directly towards or away from us, why that suddenly becomes important. Because normally you wouldn't think it affects where a star appears on the sky, right?
Right.
But with these ultra-precise measurements, it does. We want to explore what these tiny effects tell us about the stars themselves, even about whole groups of stars, like clusters, without hopefully getting bogged down in too much jargon.
Sounds good. So where do we start? Maybe the basics. What is astrometry, fundamentally?
Yeah, a good place to start. Simply put, astrometry is the bit of astronomy that's all about measuring the positions of stars and other things up there with, well, incredible accuracy.
Just pinning them down on the map?
Exactly. And also how those positions change over time. That includes their proper motion, which is their actual drift across the sky from our perspective.
Okay, their sideways movement?
Uh-huh. And also that little apparent wobble they do each year, because we're moving. As Earth orbits the sun, our viewpoint shifts, making nearby stars seem to move back and forth slightly. That's parallax.
Got it. Proper motion is the star's real drift. Parallax is the wobble from our orbit. Now, usually in what you called classical astrometry, radial velocity, the towards or away speed wasn't really part of the picture, was it? Why not?
Well, in the past, when measurements weren't quite as precise, it just wasn't directly relevant to measuring those angular positions on the sky. A star coming straight at us or going straight away isn't changing its left, right, or up-down position.
Makes sense.
And you couldn't work out its radial speed just by plotting its position anyway. The two seem quite separate.
Okay. But radial velocity is important for other things, isn't it? Like understanding the star's full journey.
Oh, absolutely essential. If you want the full 3D picture of how a star is moving through space, you need that radial velocity. Combine it with the two components of proper motion, the across the sky bit, and then, its true space velocity vector.
And that helps us understand what star dynamics.
Exactly. The kinematics, the dynamics, how individual stars move, how groups of stars like clusters orbit within the galaxy, how galaxies themselves interact. It's fundamental.
So if we can't get it just from watching the position, how do we measure radial velocity?
That's where spectroscopy comes in. We spread the star's light out into a spectrum like a rainbow.
Right.
And in that spectrum, you see these dark lines, absorption lines, which are like fingerprints for the chemical elements in the star's atmosphere.
Okay.
Now, if the star's moving towards us, those lines get squeezed a tiny bit, shifted towards the blue end of the spectrum. If it's moving away, they get stretched towards the red
The
end.
Doppler shift, like a siren changing pitch.
Precisely. And the amount of that shift tells us exactly how fast it's moving towards or away from us. The accuracy is amazing now. Big surveys get down to maybe kilometer per second.
Still pretty fast.
It is. But for looking for planets, special instruments can measure shifts corresponding to just a few centimeters per second. It's incredible.
Centimeters per second from light years away. Mind-blowing. Okay, so radial velocity is crucial, measured with Doppler shift, but it seemed separate from position. But now you're saying with really high accuracy astrometry, it links back up. How?
Yes, this is the key point from our source material. The sheer precision we have now, especially with Gaia, means these previously ignorable effects, well, they're not ignorable anymore. Even though radial velocity doesn't directly shift the star's angle on the sky at this instant, it subtly influences how its parallax and proper motion change over time.
Okay, let's unpack that. First, parallax. That's the wobble from Earth's orbit measuring distance. How does moving towards or away affect that?
Okay, imagine a star moving away from us pretty quickly as Earth goes around the sun over the course of a year, making that parallax measurement.
Right, we're looking from different spots.
Exactly. But because the star is moving further away during that year, the baseline of our measurement, the diameter of Earth's orbit, is being used to triangulate a distance that is actually increasing.
Ah, so the distance isn't constant over the measurement period.
Precisely. It introduces a tiny, tiny change in the measured parallax angle over time. And this change turns out to be proportional to the radial velocity multiplied by the square of the parallax itself.
Okay, so proportional to radial velocity times parallax squared. That means it's strongest for nearby stars, right? Because they have the largest parallax.
Exactly that. Nearby stars, especially if they also have a high radial velocity moving towards or away quickly, will show this effect most strongly. It drops off very fast for more distant stars or slower moving ones.
So the star's own motion along our line of sight adds a sort of drift to its apparent parallax wobble over the years.
A very subtle drift, yes.
Mhm.
And this isn't actually a brand new idea. The astronomer Frank Schlesinger pointed this out way back in 1917.
Wow, over a century ago.
Yeah. He realized it must happen in theory, but he also calculated that actually detecting it would need incredibly precise measurements over really long timescales, far beyond what was possible then.
Did he give an example? I think the source mentions one, Barnard's star.
He did. Barnard's star is a great case study. It's very nearby, so it has a large parallax, about 500 milliarc seconds, which is half an arc second.
Still tiny in sky terms.
Oh, absolutely.
Ah.
And it has a pretty hefty radial velocity, moving towards us at about 110 kilometers per second.
Okay.
So Schlesinger calculated the expected change in its parallax due to this effect, and it came out as just 34 micro-arc seconds per year.
Micro arc seconds, that's vanishingly small, like measuring a hair width from miles away.
Something like that.
Yeah.
Extremely challenging. But the exciting thing mentioned in the source is that Gaia's precision is actually getting down into that regime. We might finally be able to measure this century-old prediction directly.
That's amazing. So even motion straight towards or away leaves this tiny evolving fingerprint on the parallax measurement. Okay, I think I get that. What about the other part of proper motion? The stars drift across the sky. How does radial velocity affect that apparent motion?
Right, this is where the term perspective acceleration really comes into its own. Let's go back to that car analogy. Imagine a car driving away from you, but maybe slightly off to one side.
Okay.
Even if its speed is perfectly constant, the rate at which it seemed to move sideways across your view will slow down as it gets further away, won't it?
Yeah, that makes sense. Things further away seem to move slower across your vision.
Exactly. That change in apparent sideways speed is perspective acceleration. Now apply that to a star. Let's say it's moving through space at a constant velocity, partly across our line of sight, giving it proper motion, and partly towards or away from us, radial velocity.
Okay.
As it moves towards or away, its distance changes. And because angular speed across the sky depends inversely on distance, its apparent proper motion will change purely because the distance is changing.
Huh, okay. So just the changing distance makes its cross-sky speed look different over time.
That's part one. Part two is that as the star moves, the actual angle between our line of sight to the star and the star's direction of travel through space also changes.
Right, like the angle you're viewing that car from changes as it moves past.
Precisely. These two things, combined the changing distance affecting the apparent angular speed and the changing viewing angle affecting how much of its true velocity appears as motion across the sky, they result in a proper motion that isn't constant over time.
So it looks like it's accelerating or decelerating across the sky, even if its actual space velocity is perfectly steady.
Exactly. It's an apparent acceleration caused purely by our changing perspective as the star moves radially. Hence, perspective acceleration.
And what makes this effect bigger or smaller?
Well, the math shows it's proportional to the product of three things. The star's parallax, so closer helps, its proper motion, already moving fast across the sky, helps, and its radial velocity, moving fast towards or away, helps.
Okay, so again, it favors nearby stars that are also moving quickly in all directions relative to us.
That's generally where it's most significant, yes. Still a very small effect in absolute terms, but potentially measurable for the right kind of stars.
Now, if we do see a star's proper motion changing, it could be this perspective effect, or it could be, say, a real physical acceleration, maybe because it's orbiting another unseen star.
That's a crucial point, yes. Observing a change in proper motion isn't automatically perspective acceleration. It could be a real dynamic effect, like gravity from a companion star or planet pulling on it.
So how do you tell the difference?
You need more information. If it's a binary star, you look for the characteristic orbital pattern over time. But critically, if you have an accurate measurement of the star's radial velocity, you can calculate exactly how much perspective acceleration you expect to see.
Ah, so you predict the perspective part.
Uh-huh. And then you see if the observed change matches the prediction. If it does, it's likely just perspective. If there's a leftover change, that's where you might look for real acceleration, like from an orbiting companion.
Got it. So knowing the radial velocity is key to disentangling these effects. And this idea, like the parallax effect, has been around a while. You mentioned Schlesinger again.
Yes, Schlesinger actually described this phenomenon even earlier, back in 1901. It's amazing how long these concepts have been understood theoretically.
It really is. So astronomers knew about this for over a century. Did they try to measure it back then?
They did. There were some pioneering, though very difficult, attempts. The source mentions Rissenpart looking at a star called Groombridge 1830, and Lenmark and Luton trying with Barnard's star again. Always Barnard's star. It's the perfect, nearby, fast-moving target. There was even a proposal by Russell and Atkinson to use the expected perspective acceleration of a white dwarf star, Perryman 2, to try and confirm the gravitational redshift of light, a prediction from Einstein's relativity.
Wow. Using this subtle motion to test fundamental physics, did they succeed back then?
It was extremely challenging with the technology of the time. But later, using photographic plates taken over many decades, astronomers in the 1970s and 80s did manage to make measurements that seemed to confirm the perspective accelerations for Perryman 2, Groombridge 1830, and Barnard's star. It required immense patience and painstaking work.
Decades of photos, incredible dedication.
Absolutely. Then a big step came in 1999. A team led by Dravens combined data from the Hipparcos Space Telescope, the precursor to Gaia, with much older data from something called the Astrographic Catalog.
Okay.
And by comparing positions over a very long baseline, they were able to determine what they called astrometric radial velocities for 16 stars known to have large parallax and proper motion, basically inferring the radial velocity from the perspective acceleration effect itself.
Whoa, hang on. So they use the effect of radial velocity on the position changes to work out the radial velocity itself without using the Doppler shift.
Exactly. A purely geometric determination of radial velocity. Their list included Barnard's star, Kepten's star, Groombridge 1830, the usual suspect.
It's really clever, like working the problem backwards.
It is. And around the same time, specifically in 2003, another team, led by Kirster, used the Very Large Telescope to directly measure the change in Barnard's star's proper motion, the secular acceleration, and found it was consistent with the predictions based on its known radial velocity and the Hipparcos data. So the observational evidence was really firming up even before Gaia.
So these astrometric radial velocities, that's more than just a curiosity, right? Does it have deeper implications?
It really does. Think
What?
about it. Measuring radial velocity purely geometrically gives you a way to check the results you get from spectroscopy, from the Doppler shift.
Why would they be different?
Well, the Doppler shift can be subtly affected by things happening on the star's surface, like large-scale gas movements in the atmosphere convection, boiling, or even the tiny gravitational redshift effect we mentioned earlier, where light loses a bit of energy climbing out of the star's gravity well. These can slightly skew the spectral line positions.
Ah, so the geometric method isn't affected by that surface stuff. It just sees the bulk motion of the star.
Precisely. So comparing the two methods could potentially let us isolate and study those complex stellar surface effects, or confirm gravitational redshift measurements more cleanly.
That's fascinating, using this tiny positional shift to probe the physics of the star itself.
Exactly. And beyond that, it holds the potential for establishing a set of really fundamental, geometrically defined radial velocity standard stars among our nearby neighbors, a sort of gold standard reference grid, independent of spectroscopy effects.
A more robust baseline for everything else. Cool. Okay, now the source also talks about applying these ideas to whole star clusters. How does that work?
Right. So think about an open cluster. A group of stars born together, all moving through space on roughly parallel paths with roughly the same speed.
Like the Pleiades or Hyades?
Exactly. Now, if that whole cluster is moving towards us, its angular size on the sky will appear to slowly expand over time. If it's moving away, it will appear to contract.
Like that flock of birds analogy again. If they're coming closer, they look like they're spreading out.
Perfect. It's the same perspective effect, but operating on the scale of the entire cluster. The relative positions of the stars within the cluster change due to the overall radial motion of the group.
So you're not looking at individual perspective accelerations so much as the whole cluster's apparent size changing.
Primarily, yes. And there's another related effect. Because the stars were all moving together towards a certain point in space, or away from one, their individual proper motion vectors, those little arrows showing their movement across the sky, won't be perfectly parallel. They'll appear to converge towards a point in the distance called the apex of the cluster's motion, or diverge from an antipex.
Okay, like looking down railway tracks converging in the distance.
A very good analogy. The degree of that convergence tells you about the cluster's motion relative to us, including its distance and its radial velocity.
So just by measuring the proper motions and the parallaxes, the distances of the individual stars in the cluster.
You can work out the overall space velocity of the cluster, including its average radial velocity, and even get an estimate of how much the velocities vary within the cluster, its internal velocity dispersion, all primarily from astrometric data.
That's incredibly powerful, using just positions and motions on the sky to get the 3D velocity of the whole group. Has this been done?
Oh, yes. The source mentions it's been applied successfully using Hipparcos data to several nearby clusters: the Hyades, Ursa Major group, Coma Berenices, Pleiades, Praesepe. It gave valuable insights into their 3D structure and movement.
And works for globular clusters, too, those really old, dense ones.
It can, though it's often harder because they're typically much further away. But the source highlights a specific case, NGSC 3201. It's a globular cluster that happens to have quite a high radial velocity, and for a globular, a relatively large parallax, meaning it's closer than average. And using Gaia data, astronomers have actually observed the predicted perspective contraction of this entire globular cluster. Seeing that effect across hundreds of thousands of stars moving together is a pretty spectacular confirmation.
Wow. So this brings us back squarely to the space telescopes enabling all this. How big a deal was perspective acceleration for Hipparcos, and how is Gaia handling it now?
For Hipparcos, with his accuracy around 1 milliarc second, perspective acceleration was, let's say, marginal. It wasn't a dominant error source, but it wasn't entirely negligible either.
Okay.
The team identified 21 stars where the cumulative effect over the mission lifetime was predicted to be large enough, more than 0.1 milliarc seconds, that they specifically accounted for it in the final data processing, using the best available radial velocities at the time.
So a known effect, accounted for where necessary. What about Gaia, which is orders of magnitude more precise?
Right. With Gaia, it becomes much more systematically important, even still small compared to the proper motions themselves. How they've handled it has evolved with the data releases.
How so?
In the very first Gaia data release, GDR1, in 2016, the astrometric solution was still preliminary in some ways. For simplicity, and because the effect is small compared to other early uncertainties, they essentially ignored perspective acceleration by assuming zero radial velocity for all stars during that processing run.
Okay, understandable for a first pass.
Then came GDR2 in 2018, which was a huge leap in precision. For this release, they explicitly accounted for perspective acceleration, but only for 53 nearby stars that were well studied by Hipparcos and had reliable radial velocities already published in the literature.
Using existing knowledge for the most affected stars. The source had a table for this, didn't it? Showing the predicted shifts.
It did. It listed the top 10 stars where the predicted shift due to perspective acceleration over the Gaia observing period was largest. Barnard's star was right at the top, with a predicted shift of nearly 2 milliarc seconds, 1.975 MOS to be precise.
Almost 2,000ths of an arc second. Still tiny, but definitely measurable by Gaia.
Absolutely. That table really highlights the stars where this effect matters most. Then, for the more recent Gaia Early Data Release 3, EDR3, in 2020, and subsequent releases, they took a more comprehensive approach.
What changed?
They started using radial velocities measured by Gaia itself whenever possible. Gaia has its own instrument, the Radial Velocity Spectrometer, RVS, measuring Doppler shifts for millions of stars.
Oh, right. So Gaia measures position, parallax, proper motion, and radial velocity for many stars.
Exactly. So for EDR3, they incorporated Gaia's own RVS measurements into the astrometric solution to account for perspective acceleration for a vast number of stars. For some specific cases, like certain nearby white dwarfs where the RVS might struggle, they still supplemented with high-quality literature values, but the bulk relied on internal Gaia data.
So Gaia is now routinely accounting for this century-old theoretical effect using its own measurements. That's quite something.
It really is. It shows how far we've come. While perspective acceleration isn't the biggest signal Gaia sees, accurately accounting for it is essential for reaching the ultimate precision. Gaia provides this incredibly solid observational foundation for an idea that was purely theoretical for so long, and it opens the door to using that effect for deeper studies, like we discussed.
So wrapping this up, this whole dive into perspective acceleration, it really hammers home that the night sky isn't static at all, is it? There's this incredibly intricate dance going on, and seeing the subtleties requires combining super precise position measurements with knowing how things are moving towards or away from us.
Couldn't have said it better. It's all interconnected. And it really underscores the incredible value of missions like Gaia. They're not just making better maps. They're refining our whole understanding of stellar kinematics, dynamics, how stars and clusters behave, even probing the basic physics of stars themselves through these subtle effects.
It definitely makes you wonder if something as seemingly basic as a star's fixed position turns out to be this dynamic when you look closely enough. What other fundamental things about the universe might reveal hidden complexities as our instruments get even better? What other constants might actually be changing?
That's a great question to ponder. What else are we missing just because we haven't looked closely enough yet? Definitely food for thought.